I bought a broken CNC machine. Again. This is a Milltronics ML15 CNC lathe. It's basically a regular engine lathe with a couple of servo motors and a CNC control grafted onto it. The guards make it look bigger than it really is. This is a pretty small machine. It's not gonna be doing any hogging. It also has these arcade controls so you can pretend it's a manual lathe. Really not much inside the control box. There's a single board computer and a bunch of inputs and outputs, 2 servo drives and a spindle drive. Really, it's a pretty simple machine. This thing was built in 2001, and cosmetically, it's in pristine condition. It came from a college, and I don't think it's ever cut anything but air. There's not a single chip anywhere. There's not even a chip in the paint. I mean, look at the inside of this guard. There's not a scratch on it. It's incredible. This is the best looking machine I've ever owned, by a substantial margin. Let's fire it up and I'll show you the bad news. Here we go. We have this CMOS error because the battery has failed. So, let's see. Where's the delete key? Stand by, because we want to get into the setup. Well, I guess let's just go past that for now. The next problem is the screen resolution is wrong. So there's a bunch of stuff down here that we can't see. And that's, I believe, because that CMOS battery has died. I kind of need to fix that. Plus, which is that one. What's a DSTN? I think we want that one. Okay. Let's see if we can make it do stuff. It says reset drives or press escape to clear this message. Okay. There we go. It's not happy. I swapped out the little CMOS coin battery. I moved the X-axis, which was stuck on the home switch. I wonder if it will home now. Cycle start required. The X-axis, the cross slide, seems to work, but the Z-axis will not move. It sets an alarm, Z-axis excess error condition, meaning that it didn't move when the control told it to. If you swap the X and the Z, the problem moves with the drive. We have a bad servo drive. Replacements are... So I'm going to try to fix it. I'm not getting my hopes up though. From the looks of this soldering glob job, this ain't her first rodeo. Before we do that, it might be helpful to know what a servo drive is and what it actually does. A servo is just an actuator combined with a sensor. In this case, the actuator is a DC motor that turns a screw, and the sensor is an encoder. The encoder is basically a counter. It counts up and down when pulses of light pass through a slit. Encoders can be incredibly accurate. I'm only showing 30 pulses per revolution. The real encoder has 500. That might seem like a lot, but my Herco mills have 17-bit encoders. That's this many pulses per revolution. For ultra-precise applications like coordinate measuring machines, they can go up to 31-bit. That's over 2 billion pulses, 160 billionths of a degree. Don't ask me how they do it. All the servo drive does is translate commands from the CNC control, the computer, into current for the DC motor. Some people call servo drives amplifiers. That's really what they are. If you replace the CNC control with a receiver and the motor with a speaker, the servo drive would work kind of like an audio amplifier. The big difference is the encoder. It feeds back the position so the control can make corrections. That's called closed loop control. If you've ever heard of a PID control, that's basically what's going on here. To reverse a DC motor, you just swap the wires, reverse the polarity. But it actually takes 4 switches to make that happen. Instead of switches, they're using these big transistors. It's called an H-bridge, and it has kind of a fatal flaw. If these 2 transistors or these two transistors turn on at the same time, even for half a hummingbird's heartbeat, it's gonna destroy something. It's called shoot-through current, probably because of the way that it shoots through your wallet. That shouldn't ever happen, but these transistors have a nasty habit of shorting when they fail. They basically get stuck on. That's what happened here. All four are shorted. This one's actually shorted on all 3 pins. That's probably what opened up a fault line in this little chip, which appears to be a gate driver. We have 2 other problems. When they replaced the transistors, they ripped out all the plated through holes. The circuit board is just a super thin layer of copper glued to both sides of a fiberglass sheet. After they drill the holes, they use some nasty chemicals to etch away the copper, leaving the traces and a pad around each hole. Somehow they electrochemically grow a layer of copper inside the hole. That makes an electrical connection between the top and bottom layer, and it makes a much stronger solder joint. Problem is, it's only a few atoms thick. You gotta be super careful removing components. If you get a little too rambunctious, you can easily rip out the through-hole plating. Most of the time you also lift and mangle the pads and even the traces. Luckily, these are fixable. You just drill out the holes and install some of these little copper eyelets. The other problem is a lot more diabolical. These transistors, or whatever they are, seem to have a proprietary Glentek part number. There's no description, no data sheet, there's nothing. All I can find is dead-end forum posts about Glentek selling replacements for $70 a piece. I mean, there's no possible way that Glentek tooled up and made a custom transistor. They took some $2 part off the shelf and purposely obfuscated it. Luckily, I stumbled onto this post about 2 versions of a servo drive. One had the Glentek part, the other had this part number. There's no conclusion about whether or not they ended up being the same. It's also obsolete, but substitutes are not hard to find. Just to be sure, I pulled one of the transistors out of the good servo drive. It tells me it's an N-channel enhancement mode IGBT with a diode. I would say bingo was his name-o. I stuffed in a new fuse, 4 new transistors, a new gate driver, and some new thermal pads, which somehow cost almost as much as the transistors. You gotta have them though. The back plate of the transistor is electrically connected to high voltage. So you can't just use thermal paste or you'll turn the drive into a toaster. Z-axis is not happy. I was afraid of that. Blew the fuse. Something's still wrong. I did some testing with the board powered up. You gotta be extremely careful poking around these high power transistors. Bad things can happen. For example, you could accidentally bridge 2 pins, powering up the gate and forcing one surviving transistor to shoot current through the other surviving transistor, instantly destroying them both. It's probably also dangerous or whatever. I don't see anything obvious. There's a schematic in the manual, but they conveniently blocked out the transistor driver circuit, And to really twist the knife, we have another chip with a Glentek proprietary part number. This kind of feels like the point where a smart person would stop. Sunk cost fallacy and all that. Smart person probably would have stopped before buying a broken 25-year-old CNC machine. But here we are. I do love a good rabbit hole. I painstakingly reverse engineered the entire gate drive circuit. Based on similar circuits and the fact that this mystery chip was made by QT Optoelectronics, it's probably some kind of optocoupler. Its job is to isolate the peaceful analog components from the big scary transistors. It also has a somewhat unusual 3-wire output, and based on the polarity, I have a hunch it's this one. It's a pretty clever circuit. The negative voltage really makes my brain hurt. Even the simulation has a hard time with it. If you want to nerd out, I put the schematics and simulation files on GitHub for convenient AI scraping. Links below. I removed all the optocouplers and gate drivers from the board and tested the circuit on the bench. 4 of the optocouplers are now permanently coupled. But miraculously, there was a lone survivor. That's pretty lucky. I can verify the circuit works with the original components. It also works with the new optocoupler. I guess my hunch was right. Now, we have a fun new problem. It does not work with a new gate driver. I tried another slightly different gate driver, same result. Sometimes it sticks on. How is it running? It's not even plugged in. Sometimes it sticks off. Sometimes it just makes a horrible whining sound. Why? I guess we have something in common. I didn't touch anything. I don't know. We're going to skip over most of the diagnostic existential crisis. I found the problem. It was me. I couldn't get my hands on the original driver chip, so I bought a slightly different one that the datasheet reassures us is pin for pin compatible. But why doesn't it work? Well, turns out you have to read past the first line of the datasheet. These arcane symbols explain what's happening inside the chip. Don't feel bad if it looks like a bunch of hieroglyphic gibberish. I can't be the only one who's never heard of a Schottky transistor. The point is, they're not the same. Compatible? Yes. Identical? No. The computer simulation tells us what we already know. The original chip works fine. The replacement chip is unresponsive. Luckily, there's an embarrassingly simple solution. If I add a resistor, all the problems magically go away. There. That's what it should do. I don't even want to talk about how long it took me to figure that out. This rabbit hole has no bottom, so while we're down here, I'm going to re-repair the plated through holes. I wasn't happy with it. I got some longer, beefier eyelets, but they turned out to be a lot harder to install. Apparently you need a special staking tool. Oh boy. It's not perfect, but that worked way better than it should have. I really hope this works, so I'm pretty sure I'm losing my mind. Last night I had a long, vividly detailed dream about hose clamps. Alright. No time like the present. X is good. And Z is good. Look at that. It works. It finally works. I got it to home out. So let me see. Can I make it do something? Let's see. Yes. Watch this. Nothing happens. Watch this. That's what you call it, rapids? Whatever, the Z-axis is moving under its own power. We got a working servo drive. Finally. I was about to push it off a cliff. Cool. We can finally use the machine. Wonder if it needs a gear code. That'd probably be like an M41. Nothing. I think I see the problem. There we go. It does work. We got another problem. So it's telling us the spindle's turning 0.5 RPM. Remember our old friend the encoder? There's one on the spindle as well, and it does not sound healthy. That doesn't sound right. Jeepers. Loctite maybe? I don't know what they did. Well, if it wasn't broken before, it sure is now. I still can't get that shaft out of that coupling. I don't know what I'm doing wrong. Must have a big burr on the end of it or something. I don't think we can save it. The front bearing completely exploded. This used to be the disc with the optical slits. They've been erased. Might seem kind of cheesy, but you gotta have some flex because you're never gonna get perfect alignment. Yeah, this machine is a horrible mix of inch and metric fasteners. I don't know why they're still doing that. It's an American thing. We tried metric and I guess it was just too hard. Okay, I think that'll work. I wish the shaft was a little bit longer, but don't we all? I'm not crazy, right? It says pin 7 plus 5 volts, pin 8 ground. Red's on pin 7, black's on pin 8, and I have minus 5 volts. Something I'm not getting here. I swapped pin 7 and 8 in the factory connector, and I think seems to be working. Something must have got a little squirrely when they drilled this hole. I see why the bearing failed. The deeper you go, the straighter it gets. Unfortunately, Short King here just doesn't measure up. We need a longer shaft. An encoder with that kind of endowment doesn't exist, so we'll have to roll our own. Custom bracket, a dowel pin, and a quick swap from an outie to an innie. I think we can live with that. We're getting pretty close. I installed some leveling feet. One of the buttons was missing its button, I guess. I don't know what you call it. I know it cost $14. There was a screw missing from the control panel that was really bugging me, and I don't understand why this giant hole in the side of my car doesn't bother me at all. Anyway, we still cannot use the machine. The tool post, the thing that actually holds the cutting tool, sits on top of a big steel block. This one was shop made, but it looks pretty decent. The problem is it was made for the next size smaller tool post. So every dimension is just a little bit wrong. I thought it would be smart to use the tapped holes on the tool post to keep it from rotating. I mean, it just has that one stud in the center, but it didn't really work out. Right. That's not gonna work. How am I gonna get those bolts in there? Okay. Well, that's how you learn. That's okay, I'm not the only one who screws things up. Keen observers may have noticed the bigger block gained an extra hole. Whoever made it got caught in a classic measure once, cut twice scenario. They did a heck of a job hiding the evidence, though. Looks like they welded a pin in both ends of the hole. A set screw is good enough for me. I found some other problems with the tool post. The threads at the bottom of the hold down stud they're kind of mangled. It will thread in after some filing, but I don't trust it. I wanted to replace this beat up knob, and in the process I found some even more mangled threads. I don't know what happened to this thing, but I think we just found our first CNC lathe project. Right after I figure out how to write a program. I messed up. The ends of the stud are threaded to different lengths, and I forgot to change the program. Luckily, I caught it quick enough that it shouldn't hurt anything. Alright, doesn't that look snazzy? Give me a call, Dorian. I've got ideas. That's it. It does the thing. Mostly. A couple of bugs to work out, but it's a CNC lathe. Thanks for watching. What a project. I've been working on this for over 2 months. Normally, it's not that difficult to repair a servo drive. In fact, I bought another broken drive, replaced 2 transistors, and now it works fine. So I guess I've got a spare. Although if you can believe the prices, I'm tempted to sell all 3 and take a couple of months off. On that note, things have come a long way since the heyday of the DC servo drive. You can buy a brand new AC servo motor with a drive for less than I paid for that broken DC servo drive. It's 1/4 the size of the original DC motor, but it actually has slightly more torque and quite a bit more speed. Other than an order of magnitude difference in rotational inertia, there's no reason why it wouldn't work with this machine. I guess let me know if that's something you'd like to see. I don't know if I've ever seen anybody actually interface one of these new servos with an old CNC control, but I know it can be done. Also, thanks to the wonderful people who support this channel on Patreon. They make this kind of algorithmically cursed, sporadically uploaded, esoteric rabbit hole exploration a lot less perilous. That's it. Thanks again. Try not to look like you're being held hostage. Why can't I just follow simple instructions? Whatever part of my brain is needed to make a connector without f***ing things up, it isn't there.